This is the first of what will be several videos that you watch over the course of the semester designed to introduce you to new topics so that you can come to class with some basic understanding of new ideas. There really is no topic more fundamental to calculus than that of the limit. Limits allow us to make sense of things that on the surface may appear undefined. It gives us a deeper meaning to things. And the ideas in this video are perhaps some of the most important for throughout the rest of the semester. So we're going to motivate this by taking a look at a simple example. F of x is the sine of x divided by x, and divided by 2x. And we're going to assume that x is in radian measure. Everything we do in calculus, angles are always measured in radians. And there will be a time several weeks down the road when I give you a clear explanation as to why that is. So sine of x divided by 2x. Now, if we were to graph this function, we would want to find the x-intercepts. And the x-intercepts occur when the sine of x is 0. Well, the sine of x is 0 at 0, plus or minus pi, plus or minus 2 pi, and so on and so forth. But we need to wait a minute, because if we look at 0 itself, we get the sine of 0 divided by 0, which is 0 divided by 0, which is undefined. 0 divided by 0 was undefined, so even though the sine of x is equal to 0 at 0, this function as a whole does not have an intercept at x equals 0. The graph is undefined there. Now, just as an aside for a moment, if you happen to see a green rectangle pop up on your screen, that simply means the recording device is trying to refocus a little bit. So don't be concerned about that. So we have a function which is undefined at x equals 0. And on the surface, we might think that this function, therefore, has an asymptote, a vertical asymptote there, because functions like 1 over x or 1 over x squared, those functions have vertical asymptotes, and they're undefined at the origin as well. But taking a look at the graph, we see that there's something a little bit deeper going on. Here's the graph, and we can see the intercepts at 2 pi, pi, minus pi, and minus 2 pi. Now, we said that the function was undefined at the origin. So we might expect a vertical asymptote, but we can see that as we move along the graph towards x equals 0, the outputs, or the heights on the graph, are getting closer and closer to about 0.5. But on the other hand, the function is undefined at 0.5, so I really have to make sure that there's a hollow dot there. Now, I should warn you that if you use a calculator or a computer to draw a graph like this, it won't draw that hollow dot in there. We have to do that on our own, remembering that the function is undefined at the origin. We can view this numerically as well. Here's a table of values. And I did this quickly using some computer software that we might look at later in the semester. I took various x values, plugged them into the sine of x divided by 2x, and I went out many, many, many significant figures. So right here we have the x values, 1, 0.1, 0.01, 0.001, and so on and so forth. And over here we see the outputs, sine of x divided by 2x, 0.4207, 0.499916, I'm truncating, 0.499999166, blah, 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 blah. And we can see that the outputs are getting closer and closer to 0.5, very close to 0.5. And this makes perfect sense with the graph that we just looked at a moment ago. As the x values became closer and closer to the origin, the outputs became closer and closer to 0.5. And this is true if we look at negative values of x as well. Here I made a table as well using negative values of x that creep closer and closer to the origin from the left. Minus 1, minus 0.1, minus 0.01, and so on and so forth. And notice how the outputs again become closer and closer to 0.5. Well, they don't get just closer and closer to 0.5. They actually can be made as close to 0.5 as we want by choosing the x values close enough to 0, the outputs, sine of x divided by 2x, can be made as close as we like to 0.5. If I wanted to get more 9s here, or if I wanted to get something that was even closer to 0.5, I could maybe add a 0 there so that we have an x value that's closer to 0. So again, we can make the values of the sine of x divided by 2x as close as we like to 0.5 by choosing x sufficiently close to 0, but not actually equal to 0. Remember, we can't plug 0 in to the function itself. And we use notation to describe this fact. We say this in words: the limit as x approaches 0 of sine of x divided by 2x equals 1/2. So the notation in English, the limit as x approaches 0, sine of x divided by 2x is 1/2. We have the limit abbreviation here, LIM. Below we have x, and this is an arrow, approaches 0, and sine of x divided by 2x, that limit is 1/2. This is just saying precisely what we noticed in the table above, and that is, as the x values get closer to 0, the outputs get closer to 1/2. Not just close to 1/2, but we can make the outputs as close to 1/2 as we like by choosing x sufficiently close to, but not equal to 0. More generally, we can write the limit as x approaches a of f of x equals L. That means mathematically that we can make the values of f of x as close to L as we like by choosing x sufficiently close to a, but not actually equal to a. This is perhaps the single most important definition from the entire semester, and be forewarned, you'll be quizzed numerous times on to actually restate this definition. The notation is very important. Okay, in this case, the L value corresponds to 1/2. In this case, the A value corresponds to 0. And in this case, the sine of x divided by 2x is equal to f of x. So this notation is really describing what happens when we make a table of values like we did above. So in addition to knowing that very important definition, the definition of the limit, in preparation for class, what I would like for you to do is the following. I've given you some functions below. There are actually going to be 3 functions, and for each of them, I want you to explain why f of 0 is undefined. I want you to complete a table of values using x values closer and closer to 0, just like I did for sine of x divided by 2x. So again, you'll make a table of values like you did here. Use the same values of x, but of course the outputs will be different because you'll be looking at 2 different functions. This can be a little bit tedious, but if you use a calculator, it actually won't take that long. Then use your results to estimate the limit as x approaches 0 of f of x, and then sketch the graph of the function on the interval from -1 to 1. So first example, f of x is x to the third minus 10x over x squared minus 2x. Now actually, if we plug 0 in, we can automatically see that we get 0 over 0, which is undefined, but when you graph this function, you'll see that it does not have a vertical asymptote at 0. The next function is 1 minus cosine of the quantity 3x divided by x squared. And the last function is e to the x minus 1 minus x squared over 2 divided by x to the third. So for each of these 3 functions, explain why the function is undefined, complete a table of values like we did on the function sine of x divided by 2x, and use your results to estimate this limit. And I've tried to construct the examples so that the answers work out to be fairly nice numbers. And make sure you know the definition of the limit as well. Let's go back to that. The limit as x approaches a of f of x equals L means that we can make the values of f of x as close as we like to L by choosing x values sufficiently close to a, but not actually equal to a. Okay, I'll see you in class.